two equations that depend on one variable instead of one equation with two variables. Now we've always been dealing with one equation, two variables, x and y, right? Y equals 3x plus 2. Correct? That's called a Cartesian equation. So what we're used to, the y's and x's, is Cartesian. You probably haven't called it that. I'm sure you haven't over the years. That's our normal equations. Now we want parametric, which is two equations depend on one variable. They both depend on the same thing. Now, it must have parameters. What does the word parameter sound like? What does parameter mean in just real life? Parameters.
Like limit?
I couldn't understand
Like
what
a
you said.
limit?
Okay, like a limit. Maybe like, did you guys play outside when you were little?
Yeah.
Did you have parameters?
Or like a perimeter? Like a perimeter? You can't.
Like a perimeter. I have their parameters basically saying don't pass this, right? Like, oh, mine was like, you better not go past the bushes in this yard or that tree this yard. Do you have parameters and stuff like that? That's a parameter. Perimeter means it's a rectangle, but it doesn't have to be rectangle. In fact, most of them aren't, right? So parameters means you can't go past it. It's between this and this. That's a parameter. Between here and here. Yeah, that when you're a little kid, you're allowed to stay between the bushes and the driveway. Here and here. Okay, so an example of parametric equations. Oh, let me do that. I need to give you an example first. Let's make one up here. X equals 3t, y equals 4t minus 1. Where t is between -4 and 5. This is what parametric equations look like. I have two equations, but you see how they both depend on t? So t is controlling both my x and y variable. That's what's going on.
He offered us two different bases.
The little ones.
The little ones?
Yeah.
And you want these ribbons to stay on them?
No.
Okay.
Yeah. No. Yeah. Okay. So you see how x might depend on t? And t we usually use because it is usually time. As time passes, where are we on the graph? Oh, the x is at 4, the y is at 3. That kind of thing. Now, these are my parameters. Saying t has to be in between -4 and 5. If I go past that, not allowed. It's got to be in between. Saying stay in between. That's an example of parametric equations. Now, the good thing about parametric equations is they show motion and direction. They show motion and direction. And it's kind of trippy. When you graph these on your calculator, if you hit trace, you kind of scroll over, let's say you're hitting the right button, sometimes your graph will move left. It's like, what? I'm hitting the right, but my graph's moving left. Here's why. When you hit trace, it's going to trace along T. The graph may be going in a different way. It's kind of weird. I'll show you examples of that in a second. So it's kind of weird. When I was in college, I earned money as being a TA for calculus. And calculus had a lab. I know it's crazy. It was like this program called Mathematica. I hated it. It was terrible. But one of the, math professors there made the booklet, and it was just awful. But one cool thing about it is when you graph parametric equations, it showed you motion. So for instance, let's say I was graphing a circle. What it did is it was red in the beginning, wherever it started, wherever T started, and then it gradually turned to orange, yellow, green, purple. I remember my rainbow colors, purple. The rainbow gradually turned to rainbow, so you could see exactly where it started and where it ended. And if it looked like mush, you know it went around the lap more than once. It was a really cool program. But if you hit trace and it starts tracing this way, it's moving counterclockwise. So that's what I'm saying, motion and direction. Now, parametric equations are great because you can graph things that you couldn't before. How on earth would you graph that on a graphing calculator with y equals? You can't. For starters, is that a function? Doesn't pass the vertical line test, does it? Not a function. You can't graph that on your calculator with just x's and y's. You can't do it. Literally, you cannot do it with just x's and y's. Without doing 50 million piecewise functions. Like, oh, here's a piece, here's a piece, here's a piece. I mean, literally, you'd have to graph like 20 piecewise. If I'm in parametric equation form, this is very, very easy to graph. Very easy. Okay, with one statement. So that's why we need parametric equations, because not all things in life are nice, neat curves. They might be some wicked things. Alright, so let's graph this on our calculators. We're going to graph y equals x minus 1 over 2 quantity squared minus 3 on calculator. Okay, can I graph this the old-fashioned way? Just put it in our calculators under y equals. Yeah, absolutely. I can graph this, right? So yes, I all know you can graph that by literally typing it in, correct? But I'm going to show you one in the next example that you cannot do. So we're going to get creative here. We're going to use parametric equations to graph this puppy. Now, I know I'm going to have x equals y equals, and they both need to depend on t. Okay? Now look at your equation. What is your independent variable here? X, right? Because y depends on what x is. So y is the dependent, x is the independent. So x is the independent, so I'm going to let it be just t. Just t. So whatever your independent variable is, that's what I'm going to let be t. Just t, regular old t. Then y, if x is t, is t minus 1 over 2 squared minus 3. Right? If x is t, that's all I did was plug it in. Yeah? Now I need boundaries. This is where a lot of you, they're really what's going on, to be honest with you, is this. But I can't put that in my calculator. I cannot put negative infinity to infinity in my calculator. I can't do it. So what we normally put in is we put in negative 10 to 10. And if I don't see the whole graph, I make it bigger, like negative 50 to 50. We just kind of make it big as we can. Okay. Now, what I'm saying is the whole graph, what shape is this graph?
Parabola.
Parabola. It's squared, correct? So if you only see half a parabola, you're missing the graph, right? So you would make t be bigger. So let's graph this on your calculators. Go to your graph screen. Yeah, clear anything that's in there. It should have already been clear because I told calculus to clear them. See if I hit tab. Oh crap, I'm in the wrong mode. You hit tab, you have your f of x equals, right? Oh, I'm going to hurt that cow kid. I told him to put it back. I'm going to hurt that kid. I told him at the end. Put it back. You should see your f of x. I'm going to hurt another kid in calculus. Tab. Where? Where else do you graph? You graphed functions before, Scott. Yeah. Goodness
what do I do
gracious.
if I don't see it?
Well, we're going to change it anyway.
Oh.
So, it doesn't matter. Okay? That's the problem is how do I type this in? I have to change what mode I'm graphing. So, go to menu. See graph entry. What do we want? Parametric, yeah, number 3. Now, you should see x equals y equals. It's saying x1 depends on t, y1 depends on t. So here we're going to type t. I might have to do this on the board or else it'll take me an eternity. Here we're going to graph in parentheses. It was t minus 1, is that what was at the top? Yeah. All over 2. Quantity squared, and what was the rest of it?
Minus 3.
Minus 3. Now don't hit enter. Because it has parameters. Remember you got to tell between what and what? That's what I'm saying. They don't tell us the parameters here. It's assumed to be everything, but the calculator can't put in everything. So we're automatically going to put negative 10 to 10. Now it asks you what your step size is. The default is 0.13 because you're in trig actually is what's going on. I would leave it like that. You want a step size to be small. I usually use 0.1. Okay, 0.13 is close to that, so I'm not going to do it. If your step size was huge, your graph is going to look not like a curve, but more like line segments. It's going to be It's going to plot only a couple points, and we're going to do that by hand in a second. Hit enter. You should see my parabola.
Where is it now?
We'll change your window. Just go window, standard. Yeah, if you don't have a good window, just go to window standard.
I understand there's an error.
Yeah, that keeps coming as an error
Kind of error.
in the rain.
Oh, it's how did you change the symbol?
Somehow you changed the wrong symbol. Those should never change. Those did you actually really want that to happen?
Oh,
They always have to go through it.
There's no standard.
Did you find it there?
Yeah.
Okay. We good? Yes? No? Okay, let's try another one. We're going to graph this on our calculators. And here's the problem. How would you graph this before we learn parametric equations?
it's either y equal this one.
You have to get y by itself, right?
Yeah.
Go ahead and do that. Go ahead and get y by itself. What do we get? I'm asking you a trick question. You can't get y by itself.
There's a square.
Try as hard as you might, there's no way you're getting y by itself there. Factored out, you're still left with a y, correct? You can't get y by itself. So, you cannot graph this function as we know right now. Before you walked into this class today, you could not graph this, period. Now, you could complete the square. How many of you remember that? But, and most people don't remember completing the square, and it's unnecessary work because we can't use parametric equations. If I have two y's there, I can't get it by itself. I have to use a calculator. So here's what I'm going to do. X equals y equals. Which one is my independent variable?
Y.
Y. I'm going to let y be t. So then x is
T squared minus 3t.
t squared minus 3t plus 1. Now once again, t is everything, negative infinity, but my calculator, I can't do that, so I'm going to again put in negative 10, 10 on my calculator. So, on your calculators, remember you can hit delete 3 times, clear it real fast. Hit tab, and let's graph this. Let's see, it was t squared minus 3t plus 1. But don't forget to change your t. And the step size we're just going to leave. Beautiful. You didn't clear out your graph before?
No, I don't want to.
You didn't change your window either last time. Get it? And hey, that should make sense, because look at my graph. Isn't that a square? So it's it's a parabola, but it depends on y, so it's tilted, right? Not a function, but hey, look at that. I graphed a non-function. First time you've really done that. Yay! Yeah? The most common mistake people make on these is not changing their t. Negative 10 to 10 gives you usually works most of the time. Say 90-95% of the time, negative 10 to 10 works.
Is this
But if
from
you-
order calculators too?
I'm going to show you that too.
Okay.
I'm going to show you that at the end of class. Okay? Because it's a little different, but same thing. You just have to go to different places. Yeah? Okay. How about you try?
It's just red. It's just red.
Yeah, it depends on the default settings as to what color they are. Cactus, we got to when we had 4 different graphs on one screen. It was like black, pink, red, blue. Change.
It's blue and red. Looks like a fart.
Okay, how'd we do? I saw some good stuff. Some tiny mistakes, but are we good? You must know how to graph these on a calculator. Must. Now, let's graph them by hand. So we understand what's really going on. So yeah, this is on graph paper. If you wanted, we're only doing 3 graphs, so if you wanted to write on one side and graph on the other, you can. So graph the following parametric equations. We're going to check on our calculators. So x equals t. Y equals square root of 4 minus t squared. T goes from 0 to 2. You should be right. Okay, I'm going to give you some new words. They're not really new, but new in context. Initial. What does initial mean?
First.
First, the beginning. So let's think about this. If t goes from 0 to 2, the beginning is when t is 0, correct? Yes? So, I'm going to make a table here of t's. But then, remember how you first started graphing when you were little kids? You made x is 1, which makes y be this. You made a table of x and y's and then just plotted points. Kind of what we're doing now, only it's not just y. X and y both depend on t, correct? T starts at 0. Plug it in. What does x become? 0. Plug it in, what does y become? 2. Does everyone agree with that? Plug it in, I get square root of 4, which is 2. So right away, I could ask you, my initial point is 0, 2. That's where the graph starts. So if I ask you for your initial point, all you do is plug in the starting. That's all you do for the initial point. You plug in where it starts. Okay? Now, I'm going to plot that. That is the point. And notice I made my scale a little bigger because it's a tiny graph. You can do that too. I'm going to plot the point 0, 2. I'm going to plot the point. Now, I need some steps in between. I'm going from 0 to 2. What would be an appropriate step size, you think? Point 1 would be kind of little. If we were graphing on a calculator, absolutely.
So 1.
1 is very, very huge. Because think about it, I only have 3 points. 0.5 might be more. 0.5 or 0.25, those might be a little more. You want at least minimum 5 points. Minimum 5 points. So if we go 0.5, it'll give us 4. We'll go ahead and do that on this one, just to get the idea here. So we'll go ahead and do a half. When I plug it in, x is also a half, correct? What will I get here? You may use a calculator, so it's going to be a decimal. It's going to be a decimal. Someone else get that?
Yeah.
Okay, plug in 1. T is also 1. What will y become?
Square root of 5.
Square root of
No.
3, which is
Yeah.
what is a decimal. So we're graphing.
1.73.
2.
2.
Graph 3 halves, so x is 3 halves. What would y become? 0.77 something maybe?
No. 1.323.
No. You didn't plug it in. You just did 3 halves, didn't you?
I mean,
Oh no, wait, I didn't square it, did I? I'm sorry. So what do we get?
1.323.
323? Yeah, sorry, I did square mine. Okay, and then finally 2. When I plug it in, I get 2. What do I get here?
0.
0. New word. The initials when I started, this is my stopping, we're going to call it the terminal point. The terminal point is 2, 0. So if I ask you for your initial, and you don't have to graph all of it to find this, right? If I ask you for initial, you plug in your starting t. If I ask you for terminal, you plug in your ending t. So let's graph this. I didn't graph something. That's a half and 1.9. So let's see, a half and 1.9, so close up in here. 1 and 1.7, so that's kind of up in there too. 3 halves is 1.3 something. 2 is the 0.20. And of course that's not a line, right? They're not the same amount apart. So let's connect them with a curve. It's a semicircle. Ta-da! Now, if it started here and ended here, what direction is it going? Clockwise. So I could ask you another question is, what direction is it going? It's clockwise. That's what's going on. Yeah? Try another. So just write down the function. opposite directions are the same. Oh, we didn't check on our calculators. For time's sake, we're going to skip past that. Okay, so you get a few things. I think we've got that part down. Okay, once again, I'm at T, X, Y. Now, what do you think are good values for T? Yeah, but what's a good step size? We're going -3 to 3.
Is one still too big?
1 is fine, because like I said, minimum 5 data points. 1 will give me at least 5 data points, correct? Yeah. Well, over here, we have 5. That's the bare minimum. Bare minimum. Okay. So over here, we're just going to go -3, -2, -1, 0, 1, 2, 3. That'll give us at least 5. So plug in -3 into the x. What will I get? You don't need a calculator, guys. Come on. What do you get?
7.
7. Plug it into the y. What do you get? Ooh. I'm not going to change my scale on this one. No way. So by the way, my initial point is 7, -9, if I ask for it. Okay, but on the x, I go 7, -9. There's my starting point. Plug in -2, what do you get? 2, what do you get in the y? So I have 2, -6. Plug in -1, what do you get?
I get 1.
1. How about for the y? I have -1, -3. Plug in 0, what do I get for x?
-2.
What do I get for y?
0.
-2, 0. Plug in 1, I get
-1.
-1,
And 3.
3. -1, 3. We'll finish it out here. I'm going to get, let's see, 2, 6, and I'm going to get 7, 9. 2, 6, 7, 9. Now I know I started here this nice neat curve. What direction is it going? Clockwise, because I started here, right? Now, here's the thing, guys. Don't you dare have arrows. If you have arrows, it's wrong. Why? Hmm? Well, it doesn't keep going. Start, stop. Correct? If you put arrows, it's wrong because it does start and stop. Now, this should make sense because look at your graph. Isn't that a parabola? Yeah, parabola. This makes sense? Sinking in? I'm going to skip the U-turn. We'll come back to it if we have time. I want to get to one more thing. I want to find a parameterization. Big word. Big word. For the line segment with endpoints -2, 1 and 3, 5. Yeah, it's going to be weird at first, but once we do one, they're all the same. So here's what's going on. I have a line segment. Doesn't go on forever, it's just a line segment, correct? So if I were to graph this the old-fashioned way, I can't do it, because if I graph this the old-fashioned way, isn't it going to draw the entire line? Yes? If I graph this line and y equals mx plus b, it's going to draw the whole line. But I only want from here to here, so I'm going to make parametric equations. So I know I'm going to have x equals, y equals. With me so far? Okay, now I know it's going to be a line, correct? And it is a line mx plus b. But I don't want to use m and b because I need to use different. I'm going to use a and c. So I'm going to use AT plus B, CT plus D. You see that's still MX plus B? I'm just using different variables. Yeah? This is the setup all the time. This is the entire setup. I'm showing you the setup for every problem. Now, I need to have a parameter. T goes between what and what. I could pick anything I want. Any old number from here to here. I could. What would be the easiest numbers to pick? What are the easiest numbers to plug in anything? 1. Yes, there's actually an even easier one.
0.
0. 0 and 1 are the easiest things to plug in, aren't they? Yeah. So that's what I'm going to use every time. 0 to 1. You could technically use anything. But the easiest use is 0 and 1. And I'm going to use that every single time. And you can too. You use it every single time. Because here's what that's saying. Think about it. When t is 0, think about what that's saying. When t is 0, what is your x? Isn't this where I start? So when t is 0, what is your x?
Negative 2.
-2. And that 0, doesn't that say b equals -2? I solved for b. Now likewise over here, when t is 0, what's your initial y?
1.
1. Now doesn't it say b equals 1? Yeah? So let's go back up and plug in what we have. Now I have x equals at minus 2 and y equals ct plus 1. All I do is plug in b, plug in b. I'm halfway there. Now I plugged in my initial, now I'm going to plug in my terminal. So when t is 1, what is your x? Well, this is where you're stopping, right? So what is your x at the stop? 3. And doesn't it say a equals 5? Right? A minus 2 at opposite. Over here, when t is 1, what's your stopping y?
5.
So that says c is 4. Plug them back in. So I have x equals 5t minus 2. Y equals 4t plus 1. And I said t is between 0 and 1. Every problem is the same. If you learn the process, that's a very easy question. I'm going to do another one here in a second, but you see how I now have parametric equations? If I graph these on my calculator, it's just going to show me just the line segment. It's going to start and stop. Boom. Yeah? Let's try another one. 6, 5, -1, -4. 6, 5, -1, -4. Once again, it's a line segment. They're all going to be line segments. That's all I'm giving you, line segments. Start and stop. So think about as your initial and your terminal, right? Okay. So let's set it up. AT plus B, because it's a line, MX plus B. But you got to use different variables, CT plus D. So set them up as both lines. Now I'm still going to use the fact, I'm always going to use 0 and 1.
Yep.
That's easiest. So start, when t is 0, what is your x?
6.
6. Which tells me tells me b is now 6. Plug it back in. So I get a equals, or x equals, at plus 6. Okay, let's do the y. When t is 0, what's your starting y? 5. So that means d is 5. Okay, be careful. That's what I see most people do a lot. They go straight to the other x. We got to do one whole point first. So I have y equals ct plus 5. Now I'm going to use my terminal point, which is when t is 1. So when I plug in 1, what should my x be? I'm done. When I'm stopped, what is my x?
Oh,
Isn't this my start and my stop?
negative
So when I stop, I should be at negative 1. Which tells me a is now negative 7. Right? Plug it back in. X is negative 7t plus 6. Over here, when t is 1, what is your y?
negative 4.
Negative 4. Which tells me c is negative 9. So I get y is negative 9t plus 5 when I plug it back in. But do not forget your boundaries. If you leave this off, it's wrong. There will be points deducted because you have to have, parametric equations have to have parameters. Sink it in? I'm going to show you how to use the calculator and then we'll do our last U-try. But I want to show you your old calculators. You're more than welcome to come use one of mine. They're old too. Go away. I want you to move. No. Go away. Oh, I have 50 million things here. Okay, here's how to put parametric equations on your old calculators. It's pretty easy. This mine's going to take forever to boot up, apparently. First thing you do is you go to your mode, which is where you change from degrees and radians, correct? Okay, come on. I'm going to go to mode, and look at that. Parametric. So instead of function, I want parametric. And if you check out your y equals now, see how you have x and y? But here's the thing, you see how you don't have a t goes from what to what? Yeah? Don't we need that? Well, we definitely need that. We definitely need that. Remember, that's the biggest issue. People don't see the whole graph. So it's not on the same screen, but it is in window. See T-min, T-max? That's your T. Step size. Then you put in your x and y's. So it's still the same stuff, it's just in different places. Does that make sense? Okay, I want you to do